Now transformations can be combined, and this is a very important aspect of linear algebra. And it's also, as are most things in linear algebra, pretty neat. What if we follow the transformation T2 by the transformation T1? Well, first of all, if we do T2, that would take this circle and map it to this ellipse, wouldn't it? And then if we follow that by T1, if we apply this transformation to these vectors, what's going to happen? Well, you haven't proven it yet, you don't really know it, but just about what you would expect. This transformation rotates all the vectors without changing their length. Okay? So what's going to happen is this whole ellipse is going to get rotated, and it's going to get rotated about this much. Okay. Now if you accept that this rotates, we haven't proven that, but I'm actually giving it away. It does constitute a rotation. Okay, so what this does is rotate the ellipse, so that what we get, having to draw it fairly small because we don't have a lot of room here, rotates the ellipse about this much. This distance is 3, this distance is 3, so I'm going to have 3 units here, 3 units here. I'm not going to bother marking them on the axes. And then in this direction, which is perpendicular to this direction, and is going to stay perpendicular, these two directions are going to stay perpendicular because transformation T1 rotates everything by the same amount. So we're going to have kind of another axis of length 2 here and 2 here. Again, this rotates and doesn't change the length. So what we get is this ellipse, but rotated. Haven't drawn it particularly well. Okay? And there's a single matrix that represents the transformation of this to this. You don't have to do this one and then this one to get this one if you can do this. We multiply this matrix by this one. The first matrix that applies to the vector is this. And the vector, it applies to the vector by multiplying the vector on the right. Well, it's on the left of the vector. So the vector you're transforming would go here. So we'll just call this your v vector. And this matrix, the 0.8, negative 0.6, 0.6, 0.8, would multiply, or this matrix, this transformation matrix, the one we use here, would multiply this matrix to give you a matrix you would multiply by all of these vectors to directly get this. And that is also very powerful and very neat. Now, to multiply the matrices, you might know how to multiply matrices by the time you're viewing this, and you might not. You might have a sense of it, but just to either remind you or give you a little preview, it's not difficult. We just multiply the first row by the first column, second row by, or first row by the second column, second row by the first column, second row by the second column. And we put each result in the row and column that it came from. So that's quite easy to do. And I'm not going to, I don't have room to write it down, so I'm not going to do that multiplication. I might do a little addendum and put it up there on the right, and just a brief result. Now, we could also do transformation T1. We do this, And then we could do this transformation to each of these vectors. Would we get the same thing? Okay, maybe, maybe not. You're not guaranteed that you would get the same thing. It depends on the nature of the transformations. Okay, maybe for these two matrices, it works out, but it doesn't in general. And we could reduce this question I'm going to abuse the notation just a little bit. If we think of T2 and T1 as this matrix and this matrix, then the question comes down to, well, if we do T1, if we follow T1 by T2, we have to have the 2, 0 matrix, 2, 0, 0, negative 3 matrix on the left, and the 0.8, negative 0.6, 0.6, 0.8 matrix on the right. So over here, we've done T1 times T2, T1 times T2, and applied it to each vector. Over here, we would do T1, T2 times T1 applied to the vector. So we could simply reverse these two matrices and multiply them and see if the result is the same. Now I'll give you a hint, in this case it's identically the same, but that's not generally true for matrices, it's not generally true for transformations. Little terminology, you don't have to remember it, it'll come up later, but if you do remember it, it'll be even more obvious later. If these two are equal, then we say the two matrices commute, because the commutative law says the order doesn't matter. The order of the operation doesn't matter. Okay? So, these two matrices, in fact, do commute if you multiply them out. We're not going to mess with the matrix multiplication now. Just giving you the flavor of some of the things we're going to spend a long time looking at and thinking about. Okay? So, bottom line here, we can combine any two transformations. We can do one of them, get the result, and then apply the other. Sometimes it doesn't matter in which order you apply them, sometimes it does. And I should say one other thing. In general, you got two kinds of transformations. You've got transformations that rotate, and you've got transformations that stretch things in one or two directions, or maybe compress them. So, and it takes a while to develop all of that machinery to prove that it's so.